We have this wave a cos omega t minus kx. At t is equal to 0, we need to draw, let's say this is displacement. So let's say we need to find displacement, then velocity dou e by dou t and dou e by dou x versus x at t is equal to 0. Then we need to draw the velocity direction of the particles when the displacement is 0. And finally, the plot of density variation rho x. So plotting this will be quite simple. So let's do this C part first, because then when we'll plot rho x versus x, we are going to plot this along with this. So let's do A part a little bit later. So first let's find the density distribution rho x. So finding density distribution from E is equal to a cos omega t minus kx. That is our objective. So just like in the previous problem 1.55c, let's take two nearby points. So these are the 2 points that are located at a distance x and x plus dx. So obviously distance between them will be dx. And let's say the area is A. So it's a plane wave, so we are just taking a cylindrical section of that. So this is the undeformed state. When deformed, let's say this particle displaces by s and this particle displaces by s plus ds. Now let's start. So we know mass is equal to constant, so that means rho v is equal to constant. So this is always true. So if we differentiate that, we get rho dv plus v d rho is equal to 0. Or d rho by rho is equal to minus dv by v. Now you can see the actual change in volume is ds into a. So just think about it, you will understand. So this particle moved by s, this particle moved by s plus ds. So net change in volume of the cylinder will be ds into cross-sectional area A. So dv will be ds into A, and initial volume v is A into dx. So this becomes minus ds by dx. So our relation is d rho is equal to minus rho ds by dx. Now from our given equation, let's find the value of ds by dx. So that's come to be a k sine omega t minus kx. So now we can comfortably write rho. So rho can be written as the rho naught. So let's say that's the rho in the undeformed state plus change in density. So rho will be rho naught plus d rho. So if you put the value of d rho here, so that is minus rho ds by dx. So if you put minus rho ds by dx and if you take it that side, so rho will come to be rho naught upon 1 plus ds by dx. And now from 2, if you put this value, so rho comes to be rho naught upon 1 plus ak sine omega t minus kx. So this is the distribution of rho x, rho with x. So now we can plot that also along with these three. So let's do that. So our original equation is E is equal to a cos omega t minus kx. And rho we just calculated, so rho as a function of x is this. So you can imagine that density cannot become negative. And this variation in this denominator is 1 plus some sinusoidal function. So of course this sine function will reach its maximum and minimum as plus 1 and minus 1. So rho will also reach its maximum and minimum like this. But of course this is not a sinusoidal variation. It looks like sinusoidal, but it is not. It is of this form. This is of course a sinusoidal function. So E is equal to a cos omega t minus kx. So we have to plot it at t is equal to 0. So if we do that, it will come to be this. Now dou e by dou t. So if you just differentiate this will come to be this. And similarly, if you do dou e by dou x, that will come to be this. So you can plot both of these graphs also. So all of them, so this also you can see that it will start at rho naught. So at t is equal to 0 and x is equal to 0. This will be rho naught. And then if at t is equal to 0, if you increase x, t is equal to 0, if you increase x, you can see denominator will reduce. So the rho will increase. So that's what I have indicated here. So all these graphs we can plot from here. Now the B part, where we need to find the velocity variation, velocity direction of the particles at points where E is equal to 0 for cases of longitudinal and transverse waves. So since in our example the direction of the wave is towards right, so here we'll be representing the particle velocity direction with arrows. So first is longitudinal. So you can see this is the initially the wave, and then with time it will move little bit towards right. So in this transparent line is the wave just momentarily after, because wave is moving towards right. So this particle here, so we need to find the direction of the particles of the medium when E is equal to 0. Basically on this point, and this point where E is 0. So you can see that just after a moment you can see that displacement is positive. So that means the particle must have been traveling towards right, because we have taken right side as positive, because it's a longitudinal wave. And if you see this particle, so just after this moment its displacement is negative, which means it must have been traveling in negative x direction. So again this particle also must have been traveling in positive x direction. So this is the case of longitudinal waves. So in transverse waves, so same concept, just momentarily after you can see the displacement is positive, but since the wave is transverse, that means it's the arrow, we can show that its actual velocity will be upwards. So here the actual velocity of the particle is towards right, with the particle which is here, that's its velocity is towards left. Here the particle which is here, its velocity is upwards, positive, and the particle which is here, that's its velocity will be negative. All right.